one important thing that many engineering business leaders don't realize is why it is taking so much time for their team to make an efficient, complex engineering product. It seems like maybe the team is inefficient, or they are not using the right approach, or they're not spending enough time. But in my experience, one of the fundamental things which most people miss is that the team does not have a strong background in mathematics. I think that if you have access to strong mathematical tools, your team will eventually end up solving a lot of problems in an optimal fashion without having to worry about doing a lot of iteration. As an example, I remember that I once worked on a few robotics projects where we had to identify why there was a wheel slippage, or we had to identify, we actually knew why there was a wheel slippage. We wanted to identify when there was wheel slippage. And then the other instance was when there were cases where a robot was moving in a structure and there was resonance. And we wanted to understand why that was happening. Why is there this audible noise? And in both of these cases, what we did was we ended up taking all the data. So we had motor currents for the robots. We had position data, velocity data, and eventually we did a discrete Fourier transform or a fast Fourier transform in the discrete domain. And that analysis clearly showed us that there were certain spectra, and there was a specific frequency at which your robot was giving certain signatures. And by analyzing those signatures, we had a much more directed approach because we could understand, okay, if I see that certain frequency is dominant, then this is reflective of some particular submodule in my system which I know operates at that frequency and is therefore hindering the ability of my robot to work normally. Now, in many instances, I've seen that people would basically just try a bunch of things. They would do even a nice approach, like they would talk about cause and effect diagram. They might do a failure modes and effects analysis. And I talked about this in my other video about debugging systems. And while these are good approaches, they're not necessarily always going to lead you to the desired output, because without using a strong mathematical basis, it's not possible for you to solve a lot of problems in an efficient fashion, because all you'd be doing is trying out a bunch of things. And what happens in many of these situations is that people, even very experienced engineers who don't have strong mathematical backgrounds, like they might be extremely good software engineers or electrical engineers, but they don't really want to dabble with math, they don't want to get their hands dirty, they will end up finding a solution, fixing the problem, but they didn't really understand the root cause. There was no fundamental analysis, first principles analysis that was done in that case. And that means that when the problem manifests itself in a different fashion, maybe you add some submodule in the future and it starts operating at that frequency, you'll again face those problems. So I think that's the first and most important thing here. And then the second example I would like to give is where you have systems where you're trying to optimize something. So for example, let's say that you want to create a trajectory for your robot, and you want to make sure that this trajectory is time optimal. Maybe you're trying to ensure that the cost of transport for your robot is minimal, and the amount of energy that is consumed for, let's say, a legged robot per stride is very low, or the amount of the amount of motor currents that are used in that particular motion are low, or the spring force for your robot is low. In all of these cases, of course, you have to figure out first if you can make a rough model of the system, and you can identify how to reduce you can apply optimization, you can use optimal controls and figure out how to minimize the amount of each of these parameters. You can do a constrained optimization. It would be much more efficient for you to use that. And what happens many a times is that people who are not familiar with optimization theory or convex optimization will end up creating a system with some baseline and say, okay, well, it operates, right? So I guess that works for me. But if you're trying to design an optimal path for a robot, then you have to have motion planning that is using these tools, like, for example, model predictive control. And it's not just restricted to the field of robotics. So previously, like I mentioned, I've used fast Fourier analysis, I've used convex optimization, or various tools that help us understand what the most efficient algorithm for the system is. But this is something that is valid across domains. So, for example, in our solar inverters at StatCon PowerTech, we use maximum power point tracking. And the simplest algorithm for this is perturb and observe, where you perturb the system by a little bit, see where you get the maximum power. And then by doing this continuous perturbation, you're able to identify the optimal parameter for that particular period of time. Now, but this is the simplest algorithm. A lot of people use it. But again, the basis of using foundation mathematics is the principle that we applied here. So we started looking into other algorithms like fuzzy control and a bunch of other algorithms that you have in the literature, some of the proprietary algorithms that we have built, and we ended up finding something that is more optimal. And the best thing about using strong mathematics is that you don't really need to go and apply this on your system, which is what a lot of engineers do. They'll come up with something that's not really rooted in strong first principles or strong mathematics, and they will make a baseline, and they have no option but to test it on the direct system. Whereas if you have a strong mathematical system, you can use simulations, you can take a baseline model, and then you can do a lot of that analysis. So as an example, when I was working on in one of the companies where I did some projects for self-driving vehicles, we were designing motion planning algorithms and control algorithms, and a lot of that simulation that was done completely on paper. So on pen and paper, we took a model of the system, we did lateral control using model predictive control, and then we had other algorithms for controlling the system overall, and we were able to prove that given a disturbance of a certain amount, the system will be able to guaranteed to be able to get to an error of 0 and help the car move within the lane. Like, the lateral control means that you want to be within that lane. So these kind of things can be simulated, and it can be simulated everywhere. You can simulate these things in electrical design as well, and this is something we do at StatCon Electronics as well as at StatCon PowerTech. And the other thing is that it's important that no matter which field you're working in, so I talked about a few robotics projects like the kind we've done at Percho, at StatCon PowerTech, StatCon Electronics, which are power-based systems. In each of these cases, one thing that every engineer must have, I understand that some engineers may not have a strong foundation in mathematics, like they may not know optimization theory, they might not have a very good hands-on approach towards calculus. But I think statistics is fairly basic. And I've seen even advanced engineers across the world, across different continents, I've seen people not have a strong foundation in statistics. And I think that even if you don't understand how the math behind something works, when you have made a change to your system, you should definitely test it a sufficient number of times that it's statistically significant for you to come to a conclusion that the system is going to work fine. I've seen people where they would test something on, say, one power system or one robot and say, oh, I think that I tried it a few times and I ran it overnight and there were no errors, right? That's not a way to say that your system is going to work fine. You have to run it on a sufficient fleet of your systems, whether it's battery chargers or power systems or robots, and then you have to run it across a variety of configurations for a sufficient number of times. You have to take the data. You may have to overlay the plots for, let's say I'm trying to observe the motion of a motor in a specific direction, and there's one particular move where I feel like the system could fail. So if I made a change there, I'm going to make sure that once I have tracked that move, I'm going to run it across a variety of products, and I'm going to run it under different configurations, and I'm going to overlay all of them. Maybe I'm looking at motor current versus time, motor voltage versus time, speed versus time, and once I overlay, I can see what the spread is. And similarly, I can also do analysis and get like mean, standard deviation. In astronomy, people often do mean absolute deviation. And so you have to have things like these before you can say, in a statistical sense, that my system is ready to go. And this is something I have worked across multiple companies, even big names, and I've seen a lot of engineers not do that. They would just run it. They say, we gave it to QA. QA basically just tries to look for some bugs, and they're like, okay, well, I didn't see an error, so this product is ready to ship. But it doesn't really ensure that your product is going to perform optimally. It also doesn't tell you how much margin you have. Like, as an example, if you talk about control systems, you want to know how much gain margin or phase margin your system has, because that tells you how much stability your system is going to have. Because tomorrow, if there's a disturbance, it's possible that your system is not able to operate correctly. And so similarly, when you talk about embedded systems, maybe there's a loop period and you want to know how much loop period is left. If your analysis or processing in a 100 millisecond loop is going to take 95 milliseconds, then maybe there's an interrupt that comes in tomorrow, and that could make your system go haywire. So you have to have enough margin, right? So those kind of things, I think that, again, you can't just run one loop. You can't run like a loop overnight and say that it works fine. You will have to run this continuously, get sufficient data, do statistical analysis, compute the mean, median, mode, standard deviation, look at the variance, look at all these parameters before you can say that these things are fine. And there are tons of visualizations which can help you with this. You can use box plots. You can use histograms. So I think that if all engineers focused, all business leaders focused on making their teams math heavy and math savvy, a lot of their problems would start to get resolved much, much faster. And actually, because of this, at one of the companies I worked at, I started a math club. Because we were not just necessarily talking about the math that we had in our products. We were talking about just general math, because the love for the subject is what is going to give you that bent of mind where no matter what you do, you're going to try and do that, right? If you make a single change, you would at least make a scatter plot or a histogram or a box plot and figure out that the variables of interest are giving you what you're looking for. Right? Even if you can't make complex fast Fourier transform plots, you can't do optimizations, you can at least do statistical analysis. As an aside, I'm here in the beautiful Rocky Mountains, and I think that this is basically also pure mathematics, right? Mathematics is the language of nature, and I think that these are all describable using math. Maybe I'm a nerd, but when I look at this, I'd be interested in knowing, like, okay, what's the height? How does the physics of this mist work? How does the freezing of the lakes work? And I think if you have mathematically curious people in your team, people who are interested in exploring physics, then your products eventually are going to be much better. And as an example, if you think about SpaceX, right? The reason they were able to do a lot of these things is because they didn't look at the price. They just looked at what is possible with physics. And one of the things Elon Musk says is that you have to look at things from first principles. And if it's not something that is not impossible because of physics, then there's no reason we can't do it, right? And they did it. The SpaceX team was able to create reusable rockets, and that used a tremendous amount of control theory, physics, mathematics, aerodynamics, and these are all great tools which advanced mathematics can get you. So that's it. If you have more ideas on how efficiency of engineering teams can be improved, or how you've used mathematics in your company, I'd be very curious to know. Thank you.